Um, so I think this is a picture that's familiar to everyone, and I don't really have to explain it, but just urban areas are warmer, and we also know why, and we also know why certain neighborhoods are warmer than others. But although we know really well the outdoor temperature, we actually don't really know what the indoor temperature is. But people only spend 10% of their time outdoors and 90% of the time indoors. Especially during the late afternoon and the night when the urban heat island effect is the largest. They are inside, they are sleeping, and if they can't really recover well from the heat during the day, if they can't sleep very well, it can really they have a larger risk of health damages. So it's really important that we also understand what temperatures we can expect indoors. So that's what I focus on with my research. So I focus on two questions. The first one is, how does summertime indoor temperature follow the outer temperature? So in other words, how are they correlated, both in magnitude but also in time? The second question is, what is the model performance of a physics-based statistical model for summertime next day's indoor temperature? In other words, how can we model this indoor temperature with not a too elaborate model? So, uh, with my research, I first focus on the data set that I have from a couple of selected houses in the Netherlands. They have a really long measuring record, up to 27 years. And that's like later in my presentation, I will go through the results of this data set. But I first want to also say something about this. I am currently also setting up a living lab in Amsterdam. In other words, 100 crowdsourced crowd weather stations, not uh, to use the correct term for that. So that's the Net Atmo weather station. Perhaps you have heard of it. It is a weather station that has two modules. The larger one is measuring, besides temperature, pressure, and humidity, also the CO2 concentration and sound. And we put that one in the bedroom so we have a better idea, perhaps also via CO2, about ventilation in the room. And it's really that all the citizens that participate are citizen scientists. We really try to implement that. And this network is an extension of an already existing network that we have. It's called the Amsterdam Atmospheric Monitoring Supersite. It consists out of 24 outer weather stations plus a flux tower that has been running since 2014. And if you want to know more about this measurement network and some studies that we have done with it, I have a poster presentation on Thursday. And this is a map of Amsterdam with the Net Atmo weather stations that we have installed. And so far we have 80 of them installed. And this is like a very quick sneak peek in some of the measurements. So this is from the last 3 months. And I have to say, now it's of course summer in the Netherlands, and I think the warmest days are still coming. So here we see a cumulative distribution of the indoor temperature. In all the gray lines are all the individual houses, and the red line is the mean. And when we look at the threshold of 24 degrees, that's set by the WHO. If the temperature is higher than that, it's considered unhealthy. And the indoor temperature actually exceeds this for 30% of the time. And the outdoor rural reference station only exceeds this threshold for 10% of the time. And as I said, I think the warmest days are still coming, so then the difference will probably be much larger than this. So, but now coming to the data set that I've been looking at. So I aim to answer those research questions that I have on a very unique data set of hobby meteorologists with a measuring record up to 27 years. So this is on the right side. So this is a measurement done at a house in Losser. That's kind of like a rural village. And in the Netherlands, houses are relatively well insulated. They're more focused on, being warm during a cold winter and not per se cool in a hot summer. So they are relatively well insulated, they have central heating, and almost no one has air conditioning. And this house is the same. And here we see the indoor temperature and the outer temperature. And very obviously, the indoor temperature actually warms up slower and also cools down slower, which results that especially during the night, the temperature is much higher. And also when the heat wave progresses, the indoor temperature keeps rising, and after the heat wave, it kind of doesn't cool down as fast as the outer temperature. So this is, it can mean that an indoor heat wave can be longer than the actual outdoor heat wave. So for example, a health plan can be maybe longer implemented to warn the citizens. Then looking at kind of the time lag difference between temperature indoors and outdoors. So this is the time lag plot of both temperatures. For this one station, this is all 3 houses and the mean. And the purple line is the autocorrelation. The green line is the cross correlation between the indoor temperature and the outer temperature. And of course, for the purple line, so the autocorrelation, a peak is at 24 hours because a daily cycle repeats itself every 24 hours. But when we look at the cross correlation, there's a shift, and that's 270 minutes. So this is that delay in heating and cooling I was talking about, what we observe. There is a study done in Manhattan by Van Zyl and co-authors. They looked at houses, about 30 houses in Manhattan, and they actually found a similar result, only the time lag was a bit less. Then this is the same figure, but then for daily averages. So again, autocorrelation, cross correlation, and now all 3 houses and the mean. And I have to say, it's a bit difficult to say when it's uncorrelated, but after 5 days, there is still some correlation. So that means that the temperature today, during a heat wave, for example, is still correlated with the temperature 5 days ago. So there's really this delay kind of the heat wave that we also observe indoors. And the study in Manhattan found a similar results. Then this study also looked at, so imagine we only have information about the indoor temperature, nothing else. We don't know anything about how the house is built, what orientation it has, etc. Can we still model the indoor temperature? So that's what they did. They made a regression model based on outdoor conduction, building conduction, solar transfer, infrared transfer. So it only takes indoor temperature, and then from outdoors, outer temperature, outdoor wind velocity, and outdoor solar radiance. And they built this model and kind of tested it on their data. And I want to do this the same, but then for the 27 years that we have. So a little bit of a result on this. So on the left, this is the model performance. So this model predicts the change in the indoor temperature per time, and in my case, per day, and also in their case. So this here is the model performance. So the predicted change versus the actual change. And it looks alright, I have to say. It's not bad, especially for a regression model, it's not too bad. The median absolute error is 0.4 Kelvin per day. When we look at this heat wave that I also showed before, but now it's daily averages, the modeled and the observed line look quite closely together. I think there is still some room for improvement. I think looking at, for example, the solar angle compared with the main window would really improve the model, and it's not, it's quite common information that you can have about a house. Maybe also including CO2 measurements to have an idea of ventilation. So to come to the conclusions and outlook, so the first question, how does the summertime indoor temperature follow outer temperature? There is a delay, but we actually observe really high temperatures, up to 35 degrees. That was last year during summer. But for example, the WRF model, they assume a boundary condition of 20 degrees, which is of course not realistic. So it's good to have this information. Then also, what is the model performance? We found a median absolute error of 0.4 Kelvin per day. It's promising, but room for improvement. And just as an outlook, this is like the analysis that I showed. I want to apply that as well on the 100 houses that I will have after this summer, and look at, more houses than just 3 houses and see what we can find. So I'm really interested in that. And then I later also want to compare this model with a machine learning model and the WRF model, just to kind of compare how well it performs compared with those. So thank you very much for your time, and I'm happy to take any questions.
Thank you, Esther.
Yes.
Time for questions. Yes.
Hi, Oscar from UCL. I have 2 questions. First, the cumulative probability plot, is it daily or is it hourly temperatures that you showed?
This one?
Yeah, this one.
This is 10 minutes data.
10 minutes
or
data.
5 minute data, sorry. Yeah.
So, but the 24-degree threshold is probably, from the WHO, is actually probably a daily average temperature, indoor temperature. Okay?
Okay.
Yeah, I'm just saying that because
Yeah.
this is usually the metric that is used when you are looking at like indoor heat exposure that is related then to mortality, morbidity, and so on.
Okay.
And then I was wondering how you control where you put your indoor net atmo station, because you try to relate the outdoor and the indoor.
Yeah.
You have only one sensor that is given by the net atmo that is indoor. Where do you put it? Because you just said you put it in the living or the bedroom. That's fine. However, do you control the exposition of where that room is, concerning whether it is facing north, south, east, west, and so on? Because this will have a major impact on your indoor measurements of temperature. How do you control that?
Yes, so good question. Actually, we put both modules of the Net Atmo station indoors because we have this outdoor network of 24 weather stations in Amsterdam. So we take those as outdoor measurements, and the one from Net Atmo, we put both of them inside. What we do, we really personally go with the station to their house. So me and normally a student assistant, and then we are there. And what we do, we explain the project to the citizens. And then the student assistant is like taking a survey with them, so we have more information about the house. Later, after we have visited, we also send a survey online to them. And then I personally go to the rooms, well, also with them, to find a spot where we can place them. So I really make sure that they're placed at the best location that we can find within the room, so not in the direct sunlight, for example.
But this best location you're actually talking about, how do you define it? Because I'm really surprised to see an indoor temperature of 35 degrees, to be honest.
Yeah.
Is it because it was, for example, placed in the kitchen, even if it's a living room? Are there any heat sources around it? Is it because you have a window that is close by during daytime or whatsoever?
No, there's no direct sunlight, it's not close to a window. We make sure it's kind of like personal height, if it's possible, not to any heating source. So I really make sure that that's not happening. With 35 degrees, outdoors it was even hotter. So I mean, that was a really, I can explain why we observed that there. Yeah,
It'd be interesting.
Yeah.
Yeah, even in the Netherlands it can be really hot.
Yes.
So
Yeah.
we do have 40 degrees also in summer.
Yes.
So thank you, Esther. The next speaker is Legin Hu. I hope I pronounced it correctly.